Okay, let's look at question 6 from the June 2019 Limpopo question paper. The following table shows the first ionization energy for the elements of period 1 and period 2. Now remember this word period, when you see this word period, it is the horizontal lines across your periodic table. Okay, so period 1 is only hydrogen and helium, period 2 is lithium to neon. So it says to you, what is the meaning of the term first ionization energy? It's 2 marks, they just want the definition. It's the energy needed to remove the first electron from an atom in the gaseous phase. If you don't have the first, you're technically not correct, because it says to you the first ionization energy. The definition for ionization energy, that's just the definition for ionization energy, has got the removal of the word first. And then you get the second ionization energy, is the energy required to remove the second electron from an atom in a gaseous phase. So sometimes they're a bit specific with their definitions. Now it says, identify the pattern of first ionization energy in a period. So first of all, you must identify your period. Hydrogen and helium are one period. Lithium to neon is your other period. So what's happened here? 1312 goes to 2372. This is an increase. Now look at these numbers: 520, 899, 801, 1086, 1402, 1314, 16, 2081. If you look at these numbers, small, bigger, small drop, bigger, bigger, small drop, bigger, bigger. So it says the pattern. So in here, in the first period, the pattern is very obviously from left to right, the energy increases. And here, there is definitely a general increase. Yes, boron and oxygen. Is it oxygen? Slightly slip out of the pattern, but if you were to graph this from left to right, there is a general increase, and that is what they are looking for, is that there is a general increase in ionization energy from left to right across a period. Okay, so they want to know what is the pattern, and the pattern is it's increasing from left to right. Which two elements exert the strongest attractive forces on their electrons? So 2 marks for the 2 elements, 2 marks for using the data in the table to supply a reason for your answer. So the ones with the strongest forces are the ones that is going to take the most energy to remove the electron. So you look through this table, and it is helium and neon. So it is helium and neon have the strongest attractive forces on their electrons. Because why? They have the 2 highest ionization energies in the table. And it won't hurt here if you write here 2372 and 2081 kilojoules per mole, kilojoules per mole respectively. So to just prove that you know where to find them in the table, because it says use data from the table. So try and include data from the table in your answer, because it's helium and neon have the strongest forces because they've got the highest ionization energies. Explain why these 2 elements are so stable. Helium and neon are noble gases. Yes, do you agree? If you look for them on your periodic table, you will see they are noble gases. They have a filled outer electron shell, which makes them stable. So that's the sort of thing that they're looking for. You must relate it to their electron structure. They are stable in their natural state. It is safer to use helium gas than hydrogen gas in balloons. What property of helium makes it a safer substitute? Helium is not reactive, whereas hydrogen is reactive. It takes a lot of energy to change its electron configuration. So helium is safer, takes a lot of energy to change its electron configuration from its full shell structure, something like that. Mention that you know that helium is not going to react. It's stable. Helium is not reactive, so not reactive or it is stable, they are two words that you can use to indicate non-reactivity. Then it says to you, group 1 elements readily form positive ions. Is this statement correct? So there is only group 1 element, one group 1 element here if you count lithium. Okay, hydrogen is sort of group 1 but not really. But if we look at lithium, okay, this is true. Yes, it is true. Lithium has the lowest first ionization energy in the table, meaning it loses 1 electron the easiest, okay, because that's what this table means. If you only have to put in a little bit of energy to turn lithium into a lithium ion, because ionization energy is the energy to remove an electron, so lithium has the lowest first ionization in the whole energy, meaning it loses 1 electron the easiest. And hydrogen's not really a good example, but it's not really an alkali metal. But if you don't know here that group 1 is vertical, that the periods are horizontal and the groups are vertical, you will be very confused here, which is why I've said to you before, you need to know this. Okay, now let's look at the last part. When sodium atom obtains the same electronic structure as neon atom, is energy taken or released during this change? What is this change called? First of all, this change is called the first ionization energy, okay, because how does sodium get that electron structure? Sodium gets that electron structure as neon by losing an electron. That's the only way it can do it. It must lose the electron. So it's called the first ionization energy. And is energy taken in or released? Energy must be taken in, okay, because there are forces of attraction, and this means potential energy, okay? Forces of attraction mean potential energy holding the electron attracted to the positive nucleus. So energy must be provided to overcome the forces of attraction. So energy is taken in to remove the electron. So now these 5 marks, it's kind of excessive, these 5 marks. You sort of have to thumb suck, because normally it's 1 mark per fact, okay, and this is kind of a bit wishy-washy for 5 marks. I don't think this question was formulated properly, but that's the main information that they're looking for, that you need to take energy in to overcome the forces of attraction between the positive nucleus and the negative electron. So you should actually be more specific here, holding the negative electron attracted to the positive nucleus.